Welcome all. Previous class we have discussed that energy levels are quantized, and that energy levels is given by the equations that is derived from Schrodinger equations, that E is h square 8 pi square I j and j plus 1, where this j is any rotational quantum number and this is in joule. So if you change this in spectroscopy, what you're taking, the data are maximum given in centimeter inverse, not in joule. So you have to convert this joule into centimeter inverse. For that, we have already discussed that E have to discuss, because E equal to h nu, and we know that nu is, I can write by hc lambda. So this lambda I can write to E upon hc. So this is in, so this is equal to wave number, that is centimeter inverse. So we get that E equal to h centimeter inverse, we have to divide by hc. Okay, that we already discussed in previous class. So I can write E upon hc is equal to h square 8 pi square I hc j plus 1. So if I cancel it out, then I will get EHC. Let's take here, I take as E dash, then this is h 8 pi square IC j plus 1. Okay, this is the equations in centimeter inverse. These equations we have used to derive the equation energy levels, that is, let's say this is j equal to 0, and this is j equal to 1, and this is j equal to 2, and this is j equal to 3. So if you take that, if you fix the molecules, then this whole value will become constant, and let's say this is B. So for particular molecules, if you change the molecules, then this value will change because I will change. Okay, so this A, if you fix this molecules, then if we fix the molecule, then this will become E, B, J and J plus 1. This is the equations. Okay, so now these equations, we see that this energy, this A dash, so this energy depends only on J, because B is constant for a particular molecules, so only depend on J. So if you change the J from J1 to J0 to J1, then this value becomes, that is 0B, 2B, 6B, 12B. So that we know that how E equal to B, J and J plus 1. So if you J equal to 0, then this is going to be, this is 0, and this is 0 plus 1, that is going to be 0. Similarly, if J equal to 1, then it's going to becomes, let's say B 1 plus 1, that is going to be 2B. This is the E dash. So we discussed these things, and these energy levels we have derived by using these equations. So whenever you talk about of this energy gaps, between these energy gaps or between this energy gap, so how will you derive for a particular, for general energy gaps, if you want to calculate the energy gaps? The general equations for energy gap, general equations for energy gap, what you have to do, that you have to do any two difference. So this is actually E. So if I calculate any two, from higher energy level to lower energy level, then I will get the energy gap delta. It means E final minus E initial. So if I put E final, means I will take E final that is J equal to, let's say, J plus 1, and E initial I will take E J. Okay, so for any general value, so if you put that, means this value should be one higher than this value for general case if you search. Okay, so for generally this is the values, and like you have to put one more than this, because final this is the higher, from this we are subtracting this. Okay, so now that E means we know E is B, J and J plus 1. So now here we are taking J as J plus 1. So what I write here? So here I will write one thing, because E is E dash or E dash is what? B, J and J plus 1. So here if I put that E dash value, then but E dash is B and J is here J plus 1. So in place of J I will write J plus 1, and here J plus 1. So J is J plus 1. So I write J plus 1, and this is 1 again, this one, and this is the delta A. And here again that I will write here J is J itself. So I will write simply B J, J itself. And this is J plus 1. So J plus 1. So this value if I write here, then we can get this is B J plus 1, this is J plus 2 minus B, that is J and J plus 1. So if you subtract it, you see that B J plus 1 is common. So I will take B J plus 1 as common. Then what is the remaining? J plus 2. So I take that B J plus 1. So J is remain. So this one delta E, this is D J plus 1. So this cancel. Then this is remain 2. So this delta E is going to be get 2B J plus 1. So this is the general energy gap for any states. Let's say if you take and note that this J is for lower energy. Let's say that if you take the transition, so calculate the energy gap. If the question is calculate the energy gap between J equal to 0 to J equal to 1, then this J will be this value, not this value, that is the lower energy. Delta E will be, that is 2B, and J is 0 here, so 0 plus 1, that is going to be 2B. Okay, so you can see that this is this value J equal 0 J1 gap is 2B minus 0, that is 2B. Similarly, if you calculate for J equal to, let's say 2 to J equal to 3, energy gap will be, so that is delta E is 2B and J plus 1. This J is lower value, this will be 2B, and this is 2 plus 1, that is going to be 2B, and this is 3, that is going to be 6B. So if you look about of 2 to 3 gap will be 12 minus 6, that is 6B. So like this we can calculate the energy gap. Okay, so if I look the actual spectrums, that actual spectrums, how it looks. So here that observation spectra will be here, and here will be the intensity, and here that energy gap will be written, that will be this energy gap. this value here 2b, here is 6b minus 2b, that is 4b, and this is 12b minus 6b, that is 6b. So this energy gaps will be here 2b, then 4b, then we can say 6b, then if you look it is 8b, then if you look this is 10b, and if you look this is 12b. So like this energy gap will be here, this value will be this gaps, this gap 2b, 4b, 6b. So this energy gap between that. And if you notice it, that it's like here that actual spectrum how will look, here let's say this is the intensity, and this will be like this, sorry, that will be sorry for that, like this. Like that spectrums will be there, means that intensity is different, and intensity is directly proportional to populations of molecules, populations or number of molecules, populations or number of molecules present, Now another things, if you observe here that again in between that difference of this is 2b, here also you can see, here also the gap is 2b, here also you can see that gap is 2b, here also you can see gap is 2b. So always the gap will be 2b in between the observed spectra, and this spectra how will get by this is also another energy gap, and in between this energy gap that is called spectra, and this spectra also they have the equal separation, that is 2b, 2b, 2b. Okay, now so this is actually the experimental data, the spectrums look something like this. Okay, now so we are talking about this energy. So this is j equal to 0, and this is j equal to 1, and this is j equal to 2, and let's say this is 0b, this is the energy, and this is 0b, and this is 2b, and this is 6b. So what you see here is that whenever I talk about of that populations, we are talking about of the intensity, or also first let's discuss about of that selections rule. So we already discussed that whenever you are giving that any spectral lines or any electromagnetic radiations, if you give, and if we and here we have the molecules, let's say any O2 molecule, this is rotating. So after it energy, whenever it observes the frequency, and after observing the frequency means energy, because E equal to h nu, this is the frequency. So if frequency increases, then energy obviously increases. So if it observes this frequency and it shift to the higher energy, so it may be shift to here, or it may be shift to this here. So this is the context, means it will observe, let's say this is 0, so that amount of frequency it will observe, so that it will reach to 2b, or that amount of frequency it will reach, so that it will shift to 6b energy. But the selection rule, what it says, that it will be shift only to this but not to shift. So selection rule says that delta j value means j final minus j initial, that has to be either plus or minus 1, that not can be plus minus 2, not can be plus minus 3, like that. It only has to be either plus 1 or minus 1. So that's why they say the delta j value. So j final minus j initial has to be either plus 1 or minus 1. Okay, so what I see here, that the J value, this is called the selection rule. What is says that J, that is delta J, means from initial to final, or from initial to final also you can say, that is it has to be plus minus 1, means this transitions either from here, or if the transition is happening to here it will occur, or from here to here occur. This is plus 1 or this is minus 1, but it cannot be J, delta J equal to 2. So here 2 minus 0, that is 2. It can't be either this or this or this is valid. That's what the selection rule says. Okay. So another things it will arise to ask that whenever I say that this is, let's say J equal to 0, and let's say this is J equal to 1, and let's say this is J equal to 2, this is J equal to 3, and this is energy, and let's say this is 0B, and this is 2B, and this is 6B, and this is 12B, and like that you can say this is 20B, and like that this is 30B, and this is J equal to 4 and J equal to 5. Now the question is that what will be the intensity? Intensity means that is the populations that we have said, that this graphs, this is the actual spectrum. What it says that this intensity, and this is the observation spectra. Intensity directly proportional to the populations. So now when I give that electromagnetic radiations, radiations to J equal to 0, or you don't know that how the energy, means this O, let's say O2. So this is which energy, means how much it is rotating. It's rotating in a low energy, or it's rotating in higher energy, or it is rotating in very high energy, that we don't know. Let's say actually what we see, that whenever you look, let's say here, here number of CO2 is there. So 1 mole of CO2, or 1 mole of O2, let's say 1 mole of O2 means, it means what, 6.022 into 10 to the power 23 number of O2 molecule is there. So here that 6.00 into 10 to the power 23 number of O2 particles are present. So if I talk about like if I simplified it, let's say 1000, I will take as 1000 number of O2 particles are there. Actually 6.00 into 10 to the power 23 particles. For simplified, let me take 1000 number of O2 particles. So that amount of O2 particles are there, they are rotating like this, 1000 O2 particles. Like that particles are there, 1000 number of, total is 1000 O2 particles are rotating. So now the question is that this 1000 particles, is this molecules rotating only at which energy levels they are rotating? Now the question is, this amount of 1000 O2 particles are there, they are rotating, but this whole 1000 all are lie at the same energy levels, or all are lie in different energy levels? So if all are lie at only one energy level, let's say 1000 O2 particles lie only at one energy level, let's say J equal to 0, then the transitions will be occurs only when electromagnetic radiations falls to this, because here no molecules is there, here no molecule is there, full molecules are there at J equal to 0. So only transition will occur from j equal 0 to j equal to 1. But we see that transitions can occur from this j equal to 1 to j equal to 2 also. It means that full molecules are not like only one transition, only one energy level. They lie in different energy levels. Okay. So case 1, what you say that? So now we are actually finding that this 1000 number of particles are there. Let's say in uh, any sheets, if we say the 1000 number of O2 particles are there. So this 1000 O2 particles, is they are rotating at the same energy levels or they are rotating at different energy levels? If they are not rotating at the same energy levels, then how they distributed it in different energy levels? In which amount? Like at j equal to 0, it may be from 1000, if we say, then 500 or 400, or every energy level is equally distributed. That's what we want to find out. First, we say that all 1000 O2 particles are rotating at same energy levels. At same energy levels. So this condition is not get wrong, because the transition, if this condition is correct, then what? Then only one transitions only occurs. Transitions occur, that is j equal to 0 to j equal to 1. But it is not that j equal to 1 to j equal to 2 also transition is happen. So this condition is get wrong, and we will look for the next conditions. Next conditions, when we shift, when case 2, if we look, all 1000 O2 particles are distributed in different energy levels. So next case, what is that all 1000 O2 particles are distributed in different energy levels. It means, like say that 1000 totals are there. So some are there, some are rotating with low energy, some are rotating with little higher energy, some are rotating with more higher energy. Means some O2 are here, some O2 are here, some O2 are here, like that. So now the question is, if they are rotating with different energy levels, means all 1000 O2 particles are distributed in different energy levels, then how they are distributed? So now the case 1a is that all 1000 O2 particles distributed in different energy levels in same number. This is the option A. Or if they are all distributed in the same energy levels, then what you say that here, if let's say 1000, so let's hit here, let's say if you talk about of only let's say, so for generalize, although here 6.022 into 23 number of particles are there. So I'm generalizing by taking 1000 particle. So let's take, I'm taking only for 1 2 3 4 5, up to this only I'm taking, and I'm distributing everybody equally. Let's say 1000 means I will give here 200. I will give again here 200 O2 particles, here 200 O2 particles, here again I'm going to give 200 O2 particles, here again I'm going to give 200 O2 particles, because I am taking as every energy levels have equally equal number of O2 particles. If it is happens, then what happens that whenever we see that observation spectra, this is intensity, and here if you say that observation spectra, let's say here 2b, here 4b, that gap, okay, 6b, here 8b, here 10b. So this should have the equal intensity, because intensity is number of populations. So everybody should have equal intensity, because if every let's say if the transitions, if you give electromagnetic radiation, then the whole 200 will be that is shifted to this higher energy. And if you give, and again if you give the electromagnetic radiations to this, then whole 200 will shift to here. It means that the 200 number of O2 here is, O2 particle is present from j equal 0 to j equal 1. At the same time, if you give energy electromagnetic radiation, then also again the 200 will be shifted to this. It means that equal numbers of O2 particles are shifting, means that everywhere the intensity will be same. But whenever we see that actual spectrum, then actual spectrums will look like this. Somebody has high intensity, some has low intensity, and some has very low intensity. This is just for rough. Actually, it will not look like this. Actual spectrum will something, but the intensity will be different. It is not same like this. So it means that all energy levels do not have the equal number of O2 particles. Means the distribution is not equally not equal number of O2 is not distributed at every energy levels. Okay, so this condition also get wrong. Now second conditions, what you see is that then 1000 O2 particles distributed in different energy levels in different number. This is the other way. It means that they are distributed in a different numbers. So now if we say that since this is a low energy, so every molecule wants to stay with a low energy. So this has to be that what we found experimentally, that at low energy levels, there's the higher number of particles are present. Let's say if we are taking about 1000, then nearly we can say 400 particles will be here, and at j equal to 1, here will be nearly equal to here, nearly 380 particles will be there. Means this and this are approximately equal, and if you go into the higher energy levels, its energy is decreases. Let's say here 400, 380 means 780. Let's say here 50 is there, and if you got much more, then it will decreases again. Let's say it's 20. And if you decreases more, if you go more higher energy, then 10. If you go more higher energy, then you can get 5 or 2. So like whenever you go more and more higher energy levels, then getting number of molecules, or the molecules which are rotating at that energy levels, is getting lower. Means getting the number of particles rotating at that energy levels is getting lower and lower. So at the ground energy, or at the low energy, when j equals 0, higher number of molecules are rotating. So here that O2 is rotating very low, means here that O is there, this is rotating very slow. So when the molecule rotating very slow, that number of O2 is very high, and the j equal to 1, the oxygen is little bit rotating more speeds, that are nearly this is equal to this much, means 380, means nearly little bit higher energy compared to this lower energy, that is that number of molecules present, let's say 380, and some molecules which is rotating little bit fast, that are getting low 50, and the molecules which is rotating very fast, that is getting lower and lower, means high energy increases, then getting that number of O2 particles which are rotating, or any particles which are rotating at higher energy levels, that is getting reduced. Okay, so if we give the electromagnetic radiations, then if electromagnetic radiations, if we give to the lower energy levels, then the density, means the number of molecules get absorbed the electromagnetic radiations and go to the higher energy. So the number of molecules absorbed and go to the higher energy level is very high, means here we will get the high intensity. And if you go to the j equal to 1, on that time also you get equal number of like ground state. But again, if you go to the higher energy, then that number of molecules will be very less, so they observe very less intensity, and intensity will say very less intensity we find. Okay, so this how you prove that this is happening? So this is given by the Boltzmann equations. So relative populations, that will given by the relative populations distributions. But we say that whenever you take that n, let's say j, this is at the excited states and ground state, means relative population distribution. How are we doing with comparing what are doing here, that compare the, here we comparing the populations of higher energy states with respect to ground states, So whenever I see that n ground state, this is any excited states, so if I do this ratio, then what we know that n, sorry, so this nj upon ng is given by Boltzmann equation, that is E minus Ej kBT. Okay, so this is given by the Boltzmann equations. So whenever you compare the, this is the relative population distributions. So whenever you compare the populations of higher energy state with respect to ground state, that equation is given by the Boltzmann equations, that is E to the power minus Ej upon kBT. Okay, and this kBT is Boltzmann constant. This is Boltzmann constant, and this is the temperature at which the reactions we are doing, temperature at which we give electromagnetic radiations, and this is the Ej, is that E equal to B Hc. So E is Bj j plus 1. So if I put these equations here, so if I put E minus, this is that this Ej will put that if you are doing that Nj, means let's say if I doing that the excited states, let's say j equal to 1, and I'm talking about of j equal to let's say I'm going to say that nj is for j equal to 1 and n ground state is that is equal to j equal to 0. So ng means j, that is g equal to 0, means at the ground state. Okay? So this, then I will put the ej means I will put the excited state, that is nj equal to 1. So when nj equal to 1, that e is equal to b, and this is 1, and this is 1 plus 1, that is 2 upon kbt. So whenever you do this, b and kbt, so let me see that equations. So here we are talking about of the energy. So for this case, what I will put, I will not put these equations. Sorry for the wrong. So here we are talking about of the energy. So this Ej is, you know, that is h square 8 pi square I, that is j plus 1, and if I talking about of this is joule, and if I talking about of centimeters, then I will talk about of h 8 pi square I c j plus 1. So I will put this e value here. So nj upon ng, that is equal to e minus, I will put this value eh 8 pi square I c j plus 1 upon kbt. And if you put the whole the values and if you calculate it, then you will get nearly, that is equal 0.998 value, that is nearly equal to 1. It means that ratio of excited state at 1 and ground state is nearly equal to 1, means these states and these states is nearly equal to 1, means the populations available at this ground state at the excited is nearly equal to 1. Okay, and whenever you go for the next equations, when j equal to 2, and let's say nj and n ground state, that will give the e minus ej kbt. So this value will get e and this values. So now ej equal to h 8 pi square ic j and j plus 1. So now this minus h square ic, and now j is 2, so 2, that is going to be 3, and that is kbt. So this, if you calculate e h 8 pi square ic, that is 6 kbt, and if you calculate the value, it's going to be approximately 0.45, like that value, means this value, this ratio is getting decreases. Again, if you go for j equal to 3, then this nj and ground state, that is nearly equal to 0.001, like that values, means it decreases this excited this ratio. So that equation is, if you put the graphs and if you take by nj upon n ground state, what you see that, and here if you take that j values, then this value is getting, means decreasing like this, means when that this is j, when j equal to 1, the values are nearly equal, and when j equal to 2 and j equal to 3 and j equal to 4, what you see that this ratio is decreasing. If the ratio is decreasing, it means that so if the ratio is decreasing, it means that the number of molecules is very high. So compared to this value is equal same, and compared to this value is very less if the ratio is decreasing. Yes, that what it means says that if the ratio means compared to what you say, let's say that I have that 20 total whole numbers I have. So out of 20, one person has 18 and one person has let's say 10 and one person has 5. Means compared to this value is this much, and compared to this value is this much, and compared to this value is this much. Means if this value is decreasing, means this whole ratio is decreases. It means that the number of particles of getting this is decreases. That's what he said, that at the ground states, or if say the total is 1000, then let's say total is 1000, then here we will get nearly 400, here 380, here we will decreases like that, 50, here 10, like that. So this equation says that when j equal to 1, this ratio is nearly equal to 1. Let's say this is 1, and when j equal to 2, this value is decreases like this. This j value, this ratio is decreases. Okay, so this equations, and now that now what we put that so previously what you say that b has we fixed. Now if you change the b, so you see that nj on n ground state, that is equal to e minus, or if I write these equations, this equation is e, sorry, this equations is nj upon n ground state, that is equal to e minus, that is h 8 pi square I c. This is the actual equations. Okay, so whenever this and this one also, this values, if you taking the compound as fixed, so if I taking that let's say I taking the compound is fixed, then what this the value, so this value also you can write b. So now in terms of b, I can write these equations as I will write below, or let me write here itself, nj ng. If I take this value as b, then I can write e minus b j and j plus 1. Okay, so now if this value b is changed, so if you look these equations, then what you look here, I will just erase it. What you look here, nj upon ng is directly proportional to e minus b j and j plus 1. So this bj plus 1, this is actual energy. So e, this is upon kbt. Yes, this is upon kbt. So here if we say that E minus E upon ABT means if energy is increases, then full value E minus ABT this will be decreases, because if we say that E minus 2 this value is E minus 3 this value is, let's say if I write approximate this is 0. I'm just for example I'm writing 0.1, then this value going to 0.05 means this, if you increase this value then this value is going to get decreases like that. Okay, I'm just taking those for extra, not the value is not correct. If you calculate for, if you have calculator we can calculate it, means this value whenever increasing this value getting decreases and decreases. It means that if you increases E then this whole value is going to decreases. It means that whenever E increases then this value will decreases. So if it is decreases then Nj upon Nj ratio will decreases. On the other case, if that E minus 1 upon kBt, so if the T value is increases, temperature is increases, then this 1 upon kBt will be decreases again minus, then this whole value 1 upon kBt this value will increases. It means what I found here is that if I draw here, this is j equal to 0, j equal to 1, j equal to 2, this is 0, this is 2b, this is 6b. Then what we say that whenever energy is increases, then this ratio is decreases. So if we go into the higher energy, then that getting the populations will decreases. But if the temperature is increases, then on that case getting this value, this ratio will be increases. So if temperature is increases, then this ratio will increases, because this is inversion is there. Okay, so this, so if temperature is increases, then the getting the molecule here also increases, here also density will be high if the temperature is increases. Okay, that's what this equation says. And if that B changes, so what is the relations with B? You say that E minus B. So if B is high, if B is more, then Nj upon Nj value will be less, because this is in negative. So this is, let's say if I talk, this is about of 10b and then 5b. So if b increases, then this ratio will be decreases more. Okay? So that value will be 5b. 5b will be something like this. This is for 5b. 10b means if b increases, then this value will decreases. But if b decreases, then this value will be increases. Okay. So now these ratios we are taking without taking that degeneracy. Actually, what is that? Nj upon Ng ground state here. We also have that degeneracy. After that, E ABT. So here we see that this Nj upon Ng, that is directly proportional to ABT. Also this also directly proportional with G value. So here with energy increases, then this value is decreases, but this G increases, this value also increases. It means that here this value is decreases, energy terms, this value decreases with increasing in energy. But if that degeneration increases, this also increases. That will becomes like this questions. So here we can get that maxima by using that, if you calculate the maxima. Okay, so if you do that maxima by dn upon dg equal to 0 at maxima, then we'll get that the maxima value J max, where the number of intensity is high, that value we can get, that is kBT to BHC minus 1 by 2. Okay, so today up to this, thank you.